So you've completed some work already, some reading and a worksheet to talk about the cellular component of bone and what those cells do. But now I want to just help you contextualise a little bit in terms of where you actually find these cells. This is, as you already know, a very highly mineralised structure with 64% mineralised and 34% fibres and osteoid. So there's only 2% of this structure is cellular. And it's a hard, solid structure. So where do these cells lie? So we've got our two different types of bone here, as in compact or cortical bone and spongy or cancellous bone. Regardless of whatever type of bone we're looking at, even on this one here, which is a long bone, we've still got compact or cortical on the outside and cancellous or spongy on the inside. And the thought process would be easy to think that you must find these cells in these holes in the spongy part. But in actual fact, we have cells spread throughout our bone structure, whether that be compact or cortical. And the cells are within the bone itself. Now, you will find cells on the outside. You'll find your osteoblasts and your osteoclasts who are breaking down and building new bone. Certainly, you'll find them lining the outside of the cortical bone and also lining the crypts within the cancellous bone. However, our osteocytes, which control and regulate the process of bone building and remodeling, are found within what we call a Haversian system. Now, the term Haversian system was put in place because it was discovered by Mr. Haversian, but you may also hear it called an osteon. They're both the same thing, they are just interchangeable terms. So I'm going to look at one Haversian system initially and think about what it contains, and then in a minute we'll look at it kind of in context of the whole bone and it'll make a wee bit more sense to you. But basically, a Haversian system is similar to sort of the growth rings on a tree. So when the bone was first being formed or remodelled, it started off as just this first central ring. And these were osteoclasts and osteoblasts that were on the outside. And as the bone has grown and another ring has been left behind, some of the cells have got trapped in between the rings, and so on and so on. Now, this is a diagram that I've drawn, so it's only got a few rings. It would obviously get bigger and bigger and bigger. So we're going to go through and label all these structures that we're looking at on this diagram so that you can get a wee bit more context about where we're at. So the rings themselves, each growth ring is a lamella, lamellae in plural. So every time there's a bit more growth, another lamella is laid down. Then we have little crypts, little spaces between the lamellae, and we call them lacunae. And in the lacunae is where you will find your osteocytes. So they're trapped between the lamellae and the lacunae. They cannot go anywhere. They are stuck in that little crypt for the entirety of their existence. But we know that the osteocytes talk to each other. They communicate. They are the ones that decide whether bone should be built or broken down, if there's a repair that needs to go on. So whilst they're stuck in their little lacunae, they have to be able to communicate with each other and the external surface. And they do that through these tiny little canals that look a little bit like eyelashes on this diagram. And we call them canaliculi. So a tiny canal, and then iculi just means really, really tiny. So as the bone grows and more lamellae are laid down, these osteocytes get trapped, but they can still communicate with each other. And that's what we can kind of see here. These are both electron microscope images. The one on the left here being a more modern digital version, and this is an old school slide version. So this one on the left, you can see just how many processes are extending off these cells. So they are not just a straight line cell. They have lots of cell extensions that extend right into these canaliculi to allow it to be able to communicate with the next osteocyte or osteoblast or osteoclast. So that's what this one's showing here. And now this cell has been dehydrated because it's on a slide. So you can't necessarily see all the processes, but you can just about see how there's a process extending off the cell into this canaliculi, and you can certainly see it here. And they would have extended through all these as well. So it's just to try and explain to you that the cells, whilst they're stuck, are able to send messages to one another. However, these cells need nourishment. They can't just live their whole lives in this crypt and never get anything in or out to them. So that's the role of the central canal. So whilst the lamellae 1, 2, 3, and 4 in this diagram are all solid, there is a hole down the middle. It's a lumen. So that's what we call anything with space down the middle of a tube is a lumen. So this is not mineralized, it's a space. And in here, we've got everything that the bone cells need to be able to carry out their functions. So first of all, they need nutrition to be brought to them. So oxygen, vitamins, minerals, all that kind of stuff for them to be able to make up their energy. And that comes through a capillary. They then need the waste to be taken away, and that's done with a vein. It'll start off with a vein, it'll become to a really small venule. So venule is just the smallest version of a vein. They also need instruction as to what they're supposed to be doing, and that needs to come from nervous tissue. And then the last thing you'll find in here is a lymph vessel. We'll talk more about the circulatory and the lymph system later on, but a lymph vessel also serves to take away fluid and waste. So that central canal there down the middle is really, really important. Without that, the cells wouldn't be able to survive, and the cells would die off. Now, the solid structure would remain, however, it wouldn't be able to repair itself, and it wouldn't be able to know when it needed remodeled. So the central canal is really important for passing on that kind of information. So we've covered everything that's in that diagram. So now we need to think about how do these actually fit in with the rest of the bony structure. So this diagram has come from your Ross and Wilson reading, so you'll have seen it before. Basically, this is taking a sort of a cut through the larger piece of bone. So if we think about this black ring there, this is what we've been looking at so far in terms of Haversian system, but this is then packed together. So they don't sit individually, they sit in columns that run all the way through the bone. And because they're circular, there is space in between them, and that needs to be filled up. So that's filled up with what we call interstitial lamellae. They're not full rings, they're just little bits that fit in between. And you can see from this cut out section here, it's looking at the lamellae running lengthways, and you can see where the lacunae are and the little canals that allow them to communicate with each other. You can also see the central canals running through here, and they also can connect to each other and communicate because they have what we call perforating canals. So that's crossing right across the path of another Haversian system and allowing it to communicate with the next one. So you can see they all pack in together to form the solid structure of bone. Now this could be the cortical bone on the outside or the hard component of the cancellous or spongy bone as well. So it's nothing to do with the spaces. The spaces in cancellous bone are just spaces that are filled with various other structures we'll talk about later. But it's actually the solid part of bone, whether that be spongy or the compact, where you'll find these Haversian systems. And that's what allows the bone to know what's going on. It stops it being just one solid structure and allows it to have space for actual living items to dwell.